Swayam Prabha. Digital India. Educated India.
So, in the last lecture, we have briefly touched upon the idea of excluded volume interactions, that is basically, as we explained, relates to the non-bonded interactions that vary with not the distance along the contour that we have been discussing in the ideal chain model, but that also varies with the actual physical distance between 2 points on the polymer chain. Okay. And now we will see like how does this change our scaling laws that we have derived, and we will talk about something known as a good solvent and a poor solvent in more detail. Okay. So, let us just do a quick recap. So, what we have said so far is, let us say if I have a polymer chain, then if I look at say 2 points along the polymer chain, they can be very far along the contour. So, S minus S prime can be much higher than 1. So, but the physical distance is small, and the idea here is that what do we mean by small? Small meaning that whatever interactions we are considering should be important for that distance. Okay, and I will be elaborating on this particular point. So, let us call this quantity R and we'll elaborate more on this. So, the basic idea is that whatever interactions we talk about should be significantly higher than at least the thermal energy of molecules or segments. So, if the interaction is smaller than the kBT, that is I would say the scale of the thermal fluctuations, then anyway those interactions can be considered to be relatively less important or unimportant. But when the interactions are dominant, then the U of R must be much higher than kBT. Essentially, we can also think in terms of the competition between the enthalpic and entropic forces. Okay. So, the kBT is coming from the entropic forces that we have in the system. So, if the interactions are smaller than kBT or comparable to kBT, we can say that it is entropy dominated. On the other hand, if the interactions are higher than kBT, actually significantly higher, then we can say it is enthalpy dominated, and we will talk more about this as we proceed in the course. Okay. So, now before going into the specifics of what the interactions are, let us just start to visualize what exactly will happen if there are interactions present between segments far off along the chain. I gave an example in the last class of what if there is a negative charge here and a positive charge here. We can also think of in a other possibility, there can be a negative charge here or a negative charge here. The Coulomb interactions are not the only one. There can be, for example, a hydrogen bonding, we can have van der Waals interactions, whatever, right. But what will they do? Okay. So, we can actually classify the interaction at least in two broad classes. One class is the interactions are attractive, the segments have a tendency to come together, or they are repulsive, the segments repel each other. Like in the case of say minus and minus, they are like charges, they repel each other. If it is minus and plus, they want to come together. Okay? And it is not very difficult to visualize what will happen if there are repulsions between segments. If there are repulsions, then the segments want to be as far off as possible, giving rise to more stretching of the polymer chain, because segments want to be as far as possible. On the other hand, if we have attractive interactions, then segments want to be close together, and then they form like a collapsed structure. Okay? So, the one thing that is not difficult to see is for repulsive interactions, we have a stretched chain, and for attractive interactions, we have a collapsed chain. Now, the point to be made here is the ideal chain model gave us the scaling for the end-to-end distance squared average to be like RE square going to M, and that model did not consider either an attractive interaction or a repulsive interactions. So, my ideal chain is somewhere between the two extremes. My ideal chain is somewhere here, which is not as stretched as we will have in the case of a repulsive interactions, and it is not as collapsed as what we will have in the case of an attractive interactions. Okay? So, we must have the scaling law that reflects this kind of a phenomena, that the end-to-end distance must be larger when we have repulsive interactions, the end-to-end distance must be smaller when we have attractive interactions, and this must be reflected in this. And what we are going to derive now, what we will derive now is basically three scaling laws. This is for the ideal chain that follows the Gaussian statistics, and then we have something like 6 by 5 power, and all of them are like in 3 dimensions, 6 by 5 power for a chain that is stretched or swollen. So, since M is a high number, powers higher than 1, which is like 1.2 in this case, means that it will be more than the ideal chain. And then M 2 by 3 or M to the power 0.67 roughly is for a collapsed chain. Okay. So, with this background, we will actually discuss some models that predict this kind of scaling laws. But before that, I want to introduce some history here that is very interesting. So, there was a scientist, and I think I have mentioned his name in the very beginning of class. His name was Paul Flory. He was an American chemist who actually is one of the pioneers of polymer physics. So, back in the 1940s, he derived the scaling law, at least for the case of the stressed chain, and he had a very interesting and very elegant yet very simple theory based on scaling ideas that gave rise to these particular relations. Much later in 1960s and 70s, there was Sam Edwards and others in, I would say, 60s, then Dejean in, I think, 70s. They actually worked on a more rigorous theoretical treatment of polymer physics. They made more elaborate models, and based on that, the latest reference I want to cite is of a French scientist named Descloisieux, who did a much more detailed theory compared to what Paul Flory did, but got the same answer that Paul Flory had. That is not the best part of the story. The best part of the story is the theory that Paul Flory used was essentially based on wrong assumptions. So, what Paul Flory was fortunate in, or probably he had this kind of a physical intuition, that he made errors, but the errors somehow fortunately or cancelled each other, and so the end result was so perfect that not only it was demonstrated by many experimental systems, they have been proved to be true by more elaborate theories. In fact, what the Descloisieux and others, or even Dejean did, was very small, I would say less than 1 or 2%, maximum 5% change in the scaling laws for the stressed chain system. The numbers were like 1.2 compared to 2 multiplied by 0.588, that is around almost same as 1.2. Okay. So, we will start with the background that the theory is based on wrong assumptions. We will not do the detailed theories of Descloisieux. Just to tell the name, the more detailed theory is known as renormalization group theory, that is beyond the scope of this course. The physics students may have learnt about this in condensed matter physics classes and other classes. We will skip that detailed theory, we will stick with the Paul Flory theory. It contains the essential ingredients, it makes some flaws, admittedly flaws, means we know that this cannot work, but still it gives you the correct result because of some fortunate cancellation of the errors we make. And then we will take some extensions of Flory's ideas to describe the behavior of the chains here. Okay. So, before we proceed into the Flory's theory, let me also introduce the idea of like how exactly these interactions are coming into the picture, apart from the fact that you can have like a positive and negative charge or whatever. What is also extremely important is all these interactions depend on the solvent in question. Okay. So, the same polymer chain will behave differently in water as opposed to say benzene, or for a polar solvent as opposed to a non-polar solvent. So, whatever interactions we are talking about is very much solvent dependent, that is one. The second thing is whatever interactions we are talking about is very much temperature dependent. We already said that we want our interactions to be higher than kBT, that means the interactions must be higher than the entropic contribution to the energy for the interactions to have any significant effect. But now since kBT is increasing with temperature, we will also see that whatever effect we are going to have will depend on the temperature. Okay. The other way to say that is whatever measure of this non-bonded or excluded volume interactions I am going to propose will be dependent on both solvent and temperature. So, for the same reason, the first relation when we have a stretched chain is also known as a good solvent. Good meaning that in this particular solvent the polymer segments will have repulsive interactions. And just to going a bit further into what we will discuss, the chain does what is known as a self avoiding walk, that is sometimes abbreviated as SAW. And then RE square proportional to m to the power 2 by 3, that is when we have a collapsed chain. So, this is the first one is swollen, second one is collapsed, that is known as a bad solvent or a poor solvent. And then if you agree with both good and bad, then ideal chain must be in between the two extremes. Actually, we refer the ideal chain as something known as a theta solvent. So, we will talk about how they depend on the temperature a bit later, but let us talk about the solvent first. And just for instance, we take an example of water, okay? And let us see like how exactly water can change the interaction between polymer segments, okay? So, now if you think of a water molecule system, let us say you have a glass of water and you add a polymer chain into it. If you are an experimentalist, you can quickly point out that we cannot add one polymer chain. Actually, we will add many polymer chains. Let us say if I add even a 1 milligram or 1 gram, it will contain many polymer chains, okay. But let us say it is very dilute, so that we can look at a particular volume in the beaker and let us say it has one polymer chain, okay. So, here is my experiment. I start with water and I inject, sorry for the poor drawing, a polymer solution. Let me color it differently. Let us say this is my polymer solution. It is added to a beaker full of water and we mix it by some stirrer. This is my experimental arrangement. So, now of course, the polymer chains present in that droplet or the crystal, whatever we have, the form of a polymer we started with, it will get distributed. And if I zoom in anywhere in the system, if I zoom in anywhere in the system, what essentially we will have is a polymer chain that is present with water molecules, okay. And let us say it is dilute. We will talk about concentrations of polymer solutions a bit later. So, let us say if it is dilute enough, so that if I take a particular volume of my beaker, I will only see one polymer chain surrounded by solvent molecules. The water molecules are much smaller compared to the polymer molecule. Polymer molecule can have a molecular weight in thousands and water molecule has a molecular weight like 18, okay. So, they can be like surround the polymer chain. So, you will see like many of these guys surrounding the polymer chain, okay. And far off you can have other polymer chains in the system. Okay. So, what is happening, let us first look at like what is happening at a local level, and then we will think about like what is happening in the overall beaker. Okay. So, in the overall beaker, the scenario we have, if it is well dispersed, is we have polymer chains, let us say some of them which are surrounded by solvent molecules, and it is like uniformly mixed. We do not know if it is equilibrium because we have shaken it and it is like right there. Okay. So, now few things can happen. The first possibility is that the polymer chain likes water molecule, and by like it means it has some sort of favorable interaction with the water molecule, okay, and that is when we call a polymer to be hydrophilic. Philic stands for love, hydro for water. So, if it is hydrophilic, that means polymer likes water. And if it is hydrophobic, then the polymer hates water. Both these cases, the hydro part is water and the philic part stands for like, and phobic, just like the word phobia, stands for hate. Okay. So, likes means it has some sort of a favorable interactions. Okay. So, let us see like what was the scenario before we added the polymer and after we added the polymer. So, before we added the polymer, since the water is a liquid, it contains, every water molecule is forming a hydrogen bond with other water molecules. On an average, every water molecule is forming like 3 hydrogen bonds with the neighboring water molecules, and of course, the partners may change, right. So, it can be well be that, let us say this water molecule, let me draw again here the situation before we added. So, every water molecule is participating in, on an average, 3 hydrogen bonds. It can switch its partners. For example, another water molecule can come here and this bond will be gone and a new bond will be formed. So, it is not that the partners will be permanent. Water molecule can give away one water molecule hydrogen bond for another water molecule coming on its way, but every water molecules on an average wants to form 3 hydrogen bonds, because that is giving us the minimum energy state in thermodynamic sense, and this is what is the origin behind the liquid state. If I go to a vapor, we do not have a hydrogen bond. If we go to ice, we have even larger number of hydrogen bond, actually 4, and the hydrogen bonds are actually more frozen in the case of ice. Okay. So, now I have added a polymer chain into it. Now, for the polymer chain to be dissolved in water, what has to happen is the water molecules have to give up their hydrogen bonds. So, let us say now a polymer guy comes here. Now, of course, this hydrogen bond has to be sacrificed. So, earlier it was forming 3, at least those in the vicinity of the polymer chain will have lesser number of hydrogen bonds with other water molecules, and of course, they will not like it, because as I said, they are very greedy for the hydrogen bonds. They will only like it in the situation where polymer has something to offer. Okay. So, let us say if the polymer offers to form a hydrogen bond with the water molecule, let us say it has certain group let us say it has some group, let us say OH, and OH forms a hydrogen bond with O. So, in that situation, water molecule has given up a hydrogen bond with other water molecule, but now it has formed a new hydrogen bond with the polymer chain. Okay. So, the total number of hydrogen bonds of water molecule remains unchanged. Okay. So, that means that if the polymer likes to hydrogen bond with water, it can dissolve in the water easily, because water molecules can give up their hydrogen bond with other water and take the polymer's hydrogen bonds. Okay. So, in that situation we do not have any problem, but let us say the polymer does not have anything to offer. Let us say polymer does not want to participate into a hydrogen bond with water molecule because it does not have any electron donors or acceptors. In that case, now the water molecules will be unhappy to accommodate the polymer there, because they have to sacrifice a hydrogen bond with a water to accommodate the polymer chain, and they do not get anything in return. Okay. So, then in that case water molecules will try to maximize their contact with other water molecules, because they do not want to form contact with the polymer. Okay. So, if the polymer is hydrophilic, in that sense we will have more polymer water contact, and if it is hydrophobic, then we will have lesser polymer water contact, because as I just explained, in the first case every time the polymer forms a contact with the water molecules, the contact can be, let us say, a hydrogen bond. The water molecule does not have to sacrifice a hydrogen bond, it can give up a hydrogen bond with other water molecule and form with the polymer chain. Okay. And it can be that the hydrogen bond with the polymer chain is relatively more stronger compared to the hydrogen bond with the water. Okay. And I am only giving an example of a hydrogen bond. We can think about other kinds of interactions that will give rise to the similar behavior, and we can extend the idea of other kinds of solvents as well. The key point is that whenever something is a liquid, the solvent molecules have some interactions between them. So, a polymer can be accommodated if polymer has to offer some interaction to the solvent. If we have a polymer solvent interaction, in that case we have, in general sense, we can say a solvent philic polymer, otherwise it is solvent phobic polymer. Okay. So, now let us imagine that what will happen in these two cases. In the first case, the polymer chain would like to be stretched, because in the stretched case it can form more and more contacts this is a hydrophilic case. So, in this case there is perfectly no problem, water molecules can surround the polymer chain because polymer likes water. On the other hand, when it is hydrophobic, then the best case situation is water molecules will remain as it is, and the polymer is simply asked to precipitate or collapse, because when the polymer is collapsed, then you form fewer contacts of polymer with water, and in that case the water molecules have to sacrifice lesser number of hydrogen bonds. Okay. So, now let us take it a bit further and go back to the beaker. Okay. So, let us say if the polymer chain was hydrophilic, then we can have different polymer chains floating around. They are happy with their water partners and they do not worry about the other polymer chains outside in the system. Okay. On the other hand, if you have a polymer chain that is hated by the water molecules there, they want to avoid contacts with them, it will be better for the polymer chains to come together, because in that situation water molecules have to sacrifice even lesser number of hydrogen bonds. Okay. So, in that case what we see is a precipitation of the polymer chains together. What we will have in the case of a hydrophobic polymer is the polymer chains will simply settle at the bottom and the water molecules will still fill the beaker. On the other hand, this is for the hydrophobic case, this is what we know as precipitation, and in the hydrophilic case it is perfectly fine for the polymer chains to float around because they are loved by the water molecules. Okay. So, long story short, the idea is that if two people are enemy of the same person, they have to become friends together. It is not because they have some inherent attraction between them, like these polymer chains here, they do not have any inherent attraction between them, that can be possible, but since both hate water or both are hated by the water, they have to come together and become friends, because they are not being accommodated by water. Water molecules do not want to leave their water partners. On the other hand, if you have hydrophilic polymers, they are very friendly with water molecules. So, water molecules are happy to accommodate them. So, effectively the polymers need not come together because they are very happy in their company of water molecules. In the other way to state that is, the polymer molecules will not like to come together because they have to sacrifice the contacts with water, which is anyway favorable because they have hydrogen bonding. So, why will they come together? Okay. So, essentially the interactions between the polymer molecules that we see is not necessarily the interactions between molecules as such, they arise from interactions of polymer with the solvent. If polymer likes the solvent, polymer effectively repel other polymers. If polymer hates the solvent, the polymer effectively attracts other polymer. Okay? And that is why we use the word good solvent and a bad solvent. When a solvent is good, polymer likes it. When the solvent likes the polymer, when the solvent is bad or poor, it is opposite. Okay? Now, just like think of a situation that if I now raise the temperature, what will happen? If I now raise the temperature, entropy will dominate, and entropy always favors a mixed state like this. Entropy does not favor this kind of a state. So, think of like dissolving anything that is insoluble in water, let us say sugar in water, and you make tea, you always do at a higher temperature. That is because the solubility of sugar in water is higher at higher temperature, because entropy always favors mixed states or homogeneous states, and entropy always increases with temperature. Okay? So, whatever we have said about polymer solvent interactions has to be affected by the temperature, because the hydrogen bonding or any interactions will have a temperature component into them. That is one way to state that. The other way to state that is the ratio of that interaction with the thermal energy kBT, of course always depends on temperature, because thermal energy has the kBT, that is temperature inside there. Okay. That is why we use the word good, bad solvents. It has to do with the nature of solvent, and it has to do with the temperature as well, that we will elaborate in the coming lectures. So, I will stop with this and we can go with the Flory theory in the next class.